Welcome to track session number 5, Eastern track session number 5, transit systems. My name is Carlos Paradi from the University of Tokyo, and I'll be moderating today. So we have 6 presentations today, and as I mentioned earlier over email, we're going to have 14 minutes for presentations and then 5 minutes for discussion. And then the remaining 6 minutes are just the 6 minutes that you just used in the previous session, perhaps. So the first presenter will be talking about the simultaneous approach for solving the bus network design, express service design, and frequency setting problem from Hong Kong University. So, Kiang De He, I'm probably messing the names up, but if you are ready, can you share your slide?
Okay, thank you, sir. Uh, Hello, can you see the screen?
Yes, we can see it.
Okay, thank you. Hello, everyone. I'm Qian He from the University of Hong Kong. Sorry, pardon.
Also, if possible, can you turn your video on? I think it's easier for us to.
Okay. Oh, yeah, hello.
Yes, we can hear you.
Okay. Uh, Hello, everyone. I'm Qian He from the University of Hong Kong. Today, I'm very happy to be here to introduce our research project, a simultaneous approach for solving the bus network design, express service design, and the frequency setting problem. First, let me start with the introduction part. Nowadays, with the development of the suburban residential areas, non-commuting time is a common problem in large cities. About 30 commuters spend more than 1 hour to travel from home to work in Beijing, which is the capital of China, which reduces the satisfaction of the citizens. Express bus service or limited stop bus service is a potential solution to the problem. As express bus skips a lot series of bus stops and may use a faster path, the travel time can be significantly reduced. Moreover, due to the shorter circulation time, the express bus can provide a higher frequency with a limited fleet size. So with proper design, express service can bring a lot of benefits. We have reviewed the literatures related to the express bus service design, and you can see that the scale of their research is usually small, such as a single road or a bus corridor. Only one literature expands the model to a network scale. Moreover, all of these researches only consider predefined regular roads. So currently, there is no literature considering regular road design and express service design at the same stage. Besides, we also consider deadhead as a strategy to avoid overload. So the main contribution of this study are as follows. First, we propose a model to simultaneously consider the transit road design, express service design, and the frequency setting problems, while considering the capacity and the deadhead strategy. Second, we developed a modified genetic algorithm to solve the model. Thirdly, we examined all the properties of the problem and the performance of the GA algorithm. The second part of this, the second term is the problem formulation. To begin with, let me introduce the definition of the regular route and the express route in this study. In this study, regular routes have to serve every passing bus stop. No stop skipping is allowed. The road network contains several express links, such as highway or elevated road, and regular routes are not allowed to use them. One regular route has at most one corresponding express route. Every stop served by an express route is also served by the corresponding regular routes. And of course, the express routes are allowed to the express links in the network. The objective of this study is to minimize the social cost, which is the weighted sum of the passenger's travel time, the number of transfers, and the cost of the bus operator. And this is subject to many constraints, including the relationship between the corresponding regular and express routes, maximum number of stops, subtotal elimination, maximum road trip time, minimum frequency, limited free size, and no overload. Now, let me move on to the solution method. We aim to solve the bus route design, express service design, and the frequency system at the same stage. This is very complex, as a general transit network design problem without considering the frequency is already NP hard. Thus, our integrated problem is also NP hard. Thus, a heuristic or meta-heuristic is required. And in this study, we propose a modified genetic algorithm to solve the problem. So due to the time limitation, I can only show you the general scheme of the modified GA. So GA is used to determine the regular route design and the express service design, and a capacitive frequency pop algorithm is used to solve the optimum frequency setting for each GA solution. We first initialize several GA solutions and set the frequency for them. Then we generate offsprings through crossover and mutation operators. After that, a stop sequence improvement heuristic and a repair operator is used to improve the quality of the offsprings and ensure all the constraints are satisfied. We apply a nurturing technique in the survival selection to maintain the diversity of the solutions. An offspring solution will replace its parent if it's better than that parent. The process of these steps repeats for many times until the final solution is good enough. The capacitive frequency algorithm is essential in this modified GA, as we need the frequency to evaluate each GA solution. The main function of this algorithm is to allocate the fleet to each route and divide them into non-datahead buses and datahead buses. Datahead buses only serve the high demand direction to improve the frequency in that direction. A loop is built to ensure the capacity of every route is not exceeded. If some bus routes are overloaded, we have three operators to deal with. The first trial is to move buses from underloaded routes to overloaded routes and add some more datahead buses as possible. The other two are to shorten some routes and to disable some routes. To prevent endless looping, the algorithm will stop after a certain number of iterations, and then a penalty will be given. A special constraint in our study is that the regular routes are not allowed to skip any path stops. Thus, we design a waypoint mechanism. A waypoint is a special stop, and the unique sequence of the regular route can be determined based on the sequence of waypoints. The regular route is constructed by including stops along the shortest path between two adjacent waypoints and removing any duplicated stops. This waypoint scheme simplifies the planning and adjustment of the regular routes without spending much computational efforts in fixing infeasible solutions in the GA. Due to the spatial GA solution representation, we designed the specialized crossover and mutation operators. Here is the crossover operator. We exchange the local route and the corresponding express route between two parents and form the offspring solution. And this is another crossover operator, which is to exchange the sequence of the stops between two solutions. And then we have uh, totally six mutation operators that is to uh, change the change the genes for the local root and the express root as uh, respectively. Now let me move on to the numerical studies. First, we use a simultaneous to verify the ability of the GA to search the solution space. We compare the GA with the brute force method, which is to emulate all possible local and road design and express service design. We can see that the GA can reach the optimal solution within 1 minute, which is very fast compared to the brute force method. Then we applied the GA to a large network. There are totally 18 nodes and 13 terminals. The straight lines represent the regular links, and the curves represent the express links that the regular routes are not allowed to use. We compare the output solution by the modified GA for 3 approaches with different maximum number of regular routes. First, we only consider the regular route design. The minimum objective we got is 8286. When we add express service design based on the output regular route design, the base output is 7821. However, if we design the regular route and the express service simultaneously, the objective value drops to 7701. Thus, we can see that the simultaneous approach can obtain the best solution. One important difference between the sequential approach and the simultaneous approach is that 57 buses are allocated to express service in the sequential approach, while 10 more buses are allocated to the express service in the simultaneous approach. This shows that the express service by the simultaneous design is more attractive. In addition, we notice that there is a difference between the optimal number of regular routes with and without the express service. The benefit of adding express service based on an optimized 12-route regular bus network would be minimal. Thus, we suggest that when adding express service on an existing irregular transit system, the regular routes should also be redesigned at the same stage. We also test the effect of some parameters, and we can see when the minimum frequency increases, the number of available rows average waiting time drops, while the number of passengers needed transfer, and the main objective value increases. Thus, the frequency constraint should be carefully determined based on the trade-off between the waiting time and transfer. In conc so let me conclusion. First, we propose a model to formulate the transit route design, express service design, and the frequency setting problem with the capacity constraint and the data head strategy. A modified genetic algorithm was developed to solve the model. Several specific operators are designed for the investigated problem. The numerical experiments shows that introducing express service can significantly reduce the total social cost. In addition, the simultaneous approach to design the regular routes and the express service can output a better solution than optimize the express service based on a predefined regular routes. Okay, that is all of my presentation. Thank you.
Oh, thank you very much. There's a question in the chat. Does the model account for the possible different operating schedules of regular and express buses? For example, in Singapore, express buses operate only during peak hours on specific days. Will this affect the route design?
Uh, in So the express service should be applied when only when the uh, patch, patching flow is large enough. So in this study we just use the data in the peak hours, and of course, so the whether to apply the express service on during the normal time should be re-evaluated whenever considered. Yes.
Okay, thank you. If there are any other questions, please write them in the chat. I have it's more a clarification. You talk about the deadhead strategy, but I think I didn't catch the meaning of that. So can you explain with a bit more detail about that consideration of the deadhead strategy?
Uh, so say find so in the network, this is a urban to suburban to urban network. So in the morning peak, we consider that more passengers will travel from the suburban to the urban, and the, due to the due to the different passenger flow in mm, dif different directions. So the deadhead buses only travel from the suburban to the urban and will return to the suburban without carrying any passengers. That can increase the frequency with a limited fleet size.
So what is it? So okay, so how do you consider this in your strategy then? How do you avoid or minimize that? So you just resend the buses to a different route?
So we will uh, we cons we consider we can for each route we will consider several buses are dedicated buses and several buses are non-dedicated buses. Some will serve both direction and some will only serve one direction. And we consider the cost of the bus operator and how to uh, uh, collect allocate the fleet size is based on the final total social cost.
Okay, thank you very much. Are there any other questions? If not, then I would like to wrap it up here. Thank you very much.
Thank
And
you.
go on to the next presentation. It's also about bus network design by Mr. Liu or Miss Liu. So whenever you're ready.
Uh, Hi, can you see the screen?
Yes, we can see the screen. Can you turn your video on, please?
Um, okay. Um, uh, I'm sorry, the Zoom said it cannot detect my camera. I don't know
Uh,
what's
no, okay, we don't have time.
wrong.
So let's just do it like this.
Oh, okay.
Okay.
Good afternoon, everyone. My name is Liu Mingrui from the University of Hong Kong, and the title of my presentation today is Bus Network Design with the Integration of Limited Stop and Autonomous Bus Services. And then let me first introduce the importance of public transportation network design and operation. The The public transportation networks are vital for mobility of people in metropolitan cities, e- especially for suburban residents. The design and operation of these networks are crucial in providing efficient and convenient travel to central work and entertainment districts. Um, Innovative network designs and operation strategies improve passengers' travel experience by offering diverse options for commuters and enhancing travel efficiency through optimized routes. These approaches also contribute to sustainability while achieving significant cost savings by streamlining operations. To improve the transportation service quality, innovative public network design and operations are being introduced. One effective method is to enhance the level of service is through the implementation of limited stop lines. These lines make fewer stops than normal lines, striking a balance between faster travel times and serving key intermediate stops. Additionally, express lines can be established to provide fast and direct service between 2 points, catering to areas with high demand for quicker travel times. By combining these line patterns, public transportation systems can offer a diverse range of options and enhance the overall passenger experience. Previous literature solved the limited stop service design problem in explicit or not explicit ways. For example, labor design limited stop service not in explicit way, which means constructing limited stop lines by selecting from predetermined candidate limited stop lines. However, the limited stop design is not explicit. Since this kind of candidate lines selection is not able to obtain the real best pattern. Some researchers, for example, once started to solve this design explicitly, which corresponds to making the decision for every intermediate stop about whether to skip this intermediate stop or not for all limited stop lines. Bus networks with different numbers of limited stop lines correspond to each normal line are designed by researchers. Lever et al. And Wang et al. Consider unlimited numbers of limited stop lines corresponding to each normal line in their network, while Lever discussed that there are minimal benefits of constructing more than two limited stop services along one normal line. Therefore, one way to improve network design can become that each normal line is accompanied by one corresponding limited stop line. However, introducing more lines causes more buses to run, which increases operators' cost. To handle this problem and the limitation of operators' budgets, autonomous buses are considered to save operators' costs since autonomous buses are driver-free. Some studies in the literature discuss the beneficial aspects of autonomous buses. Zhang et al. Finds that fully autonomous buses offer significant cost savings. It can be concluded that it costs operators more to incorporate limited stop services and more cost-saving autonomous buses were not considered in previous research. While we also can notice that even if incorporating autonomous vehicles can bring benefits to the public transportation system, passengers are concerned about the safety issues. To our knowledge, the integration of both limited stop and autonomous services has not been researched. Consequently, considering both limited stop services and autonomous bus services make use respective advantage of each service and bring benefits for both operators and the passengers. And these are there are three main objectives of this work. The first is that this is the first research considering both limited stop and autonomous bus services. And second, we develop a mathematical formulation and design a specific GA to solve this problem. And the third, we implement experiments to show the effectiveness of this kind of integration and conduct sensitivity analysis to demonstrate suitable scenarios and provide policy insights. And then let's move on to the formulation part. The objective function is to minimize the weighted sum of first, total passenger travel time, second, number of transfers, and third, the total operator's cost. The first three constraints are line start, end, and stop connectivity constraints. And those two, constraints 5 and 6 guarantees one stop can be visited by one normal line once at first, at most. Constraint 7 calculate the line travel time. Constraints 8 and 9 are the conventional and the autonomous but free size constraints. 10 and 11 set requirements for minimal and maximum frequency. Constraint 12 limit the maximum number of intermediate stops for normal bus lines. So constraint 13 guarantees that limited stop bus lines must skip at least one bus stop, and constraint 14 is the vertex covering constraint. The constraint 15 define the indicator of whether line N visits both I and J. Constraint 16 calculate travel time from I to J. Constraint 17 is also an indicator, and constraint 18 limit the maximum in-vehicle traveling time, and constraint 19 calculate the average travel time from I to E. And constraint 20 and 21 defines the relationship of cost structure between autonomous and the conventional buses. Constraint 20 and 23 are the limited stop bus lines start and end at the same stops as the corresponding normal bus lines. And the last constraint guarantees that limited stop bus lines must visit the subset of the stops of corresponding normal bus lines. And having constructed the formulation, we develop solution methodology to solve this formulation. And the figure on the left is the flowchart of the GA we developed. And there are three main new features of the modified GA. The first is that we develop a vehicle assignment heuristic based on line search to solve frequency setting problem. The second is that a line pattern heuristic is integrated to solve the line pattern design problem. And the third is that we develop autonomous line selection heuristic and autonomous bus lines selection mutation operators to solve the autonomous bus lines determination problem. And having developed the algorithm, we use this algorithm to implement numerical experiments. The figure on the left represents Tingshui residential area and Tingshui public transportation network. Depicted in this figure, there are square nodes representing locations that serve as both bus terminals, and while circle nodes indicate existing bus stops, and there is one bus interchange on the southeast side of this residential area, and there are three urban destinations outside this residential area. And then we first um, demonstrate the effectiveness of integration of kind of this kind of integration. And as can be seen in this table, compared to base case, total passenger travel time decreases and the operator cost increases after the integration of limited stop lines. While limited stop lines are considered passenger traveling by limited stop lines can save both detouring and dwelling time compared to traveling by normal lines, so that the total passenger travel time decreases. However, due to the planning of more lines, more conventional buses need to be operated on the network, resulting in larger operator cost. Compared to the base case, while autonomous buses are also considered in scenario 3, the total passenger travel time increases because of the slower speed of autonomous buses. However, the autonomous buses are cheaper than the conventional buses, so the operator cost gets lower. And in scenario 4, both advantages of limited stop lines and autonomous buses are integrated so that the objective value is the smallest one. Compared to the base case, the total passenger travel time and the operator cost both get lower. Therefore, integrating both limited stop and autonomous bus services to the public transportation network is beneficial for both passengers and operators. Since the nature of optimization problem is multi-objective, the value of travel time is of significance for the trade-off between the total passenger travel time, number of transfers, and the operator costs. Replicates of this experiment with different values of travel time are implemented. The results of this numerical example are given in these two figures, and it can be seen in this figure on the left that when the VTT gets lower, the total passenger travel time has the tendency to increase, and the operator cost has the trend to decrease, because when VTT becomes smaller from 120 to 40 Hong Kong dollars per hour, which means the passenger travel time gets less significant to the objective value, so that some of the conventional buses are replaced by the more cost-saving autonomous buses. When BTT becomes even lower from 40 to 20 Hong Kong dollars per hour, no more conventional buses can be replaced. So the number of autonomous buses is getting lower in order to save operator cost. The figure on the right shows the change in the number of conventional and autonomous buses. Consequently, in economically developed regions where the BT has a higher level, more conventional buses and less autonomous buses should be operated. While in moderately developed regions where the VTT has a medium value, for example, around 40 Hong Kong dollars per hour, the number of autonomous buses that should be operated reaches the peak value. And finally, the following are the conclusions First, this study investigate the public transportation network design and frequency setting problem, considering limited stop and autonomous bus services. Second, we design a hybrid GA to solve this problem. And third, we implement experiments to demonstrate the effectiveness and contact sensitivity of value of travel time. And that is the end of my presentation today. Thank you for your attention.
Thank you very much. I don't see any questions in the chat yet, but if there are any questions, please post them. I want to ask you about the cost structure between so autonomous buses and regular buses. So you mentioned that they are cheaper.
Yes.
So can you elaborate in that? Because I would assume that at least I don't know what is the human resource cost in Hong Kong, but I would assume that the LiDAR technology or the vehicle itself it's very expensive. So can you elaborate on your assumptions for the cost structures?
Yes, the total cost uh of of one autonomous bus is cheaper than conventional bus. Um, Actually, the ownership is of autonomous buses um is larger than the conventional bus, but the operating cost
Mm.
of the autonomous buses is cheaper than the conventional buses because it's driver free, and we identify that together, and the result is that the the total operating cost of one autonomous bus is cheaper than than one conventional bus.
Yeah, so my question is about the sources of those costs, right? So is this like actual market prices? I'm
We
not familiar with the with autonomous vehicles running at the moment, right? So,
I cite this in one paper. I said this is from another paper.
but is that it's okay? But are those actual values? Are those just like estimated values? Are just like that's what I want. I want to elaborate on your assumptions here.
I think
So
it's I think it's a it's a real it's a real real data. Yeah. Real
real
data.
original
Yeah.
data.
Yes.
Okay.
It's not artificial.
Okay.
Yeah.
If possible, can you share the paper in on the chat later? It'll be interesting reference. Okay, no questions on the chat yet. So the other thing is like, so the key difference between in the whole model will be essentially the cost structure, right? What differentiates an autonomous bus from a regular bus is essentially that, right? There are no operational differences in terms of the autonomous bus, right? Other than cost.
Uh, no, there is one more difference. It, the which is that the autonomous buses run slower than the conventional
Oh,
buses.
okay.
Yes.
Do you have data on that as well? Actually, yeah, now that you mentioned it, they're not that fast. So how much slower are they?
We use three different values, like 1.1, 1.2, and 1.3. The ratio
Okay, it's just a ratio. Okay.
of uh, the ratio, yeah,
And
the
are
ratio
these
of the
values
speed.
also assumed, are just assumed, or they're also based on empirical observations?
These are assumed, yeah.
Okay. Okay, are there any other questions from the audience? Okay, there don't seem to be any other questions, so I would like to wrap it up here. Thank you very much.
Okay, thank you.
Okay, so moving on to our third presenter, talking about older adult satisfaction with multimodal transit services and attribute performance, Hao Seng Yang, whenever you're ready.
Okay. Hi, Professor.
Hi, and if possible, can you please turn your video on?
Okay. Professor, can you see my slides?
Yes, can you put them
Yeah,
in
okay.
full screen?
Okay.
Oh,
Okay.
great.
Hi, everyone. My name is Yang Haosen, and I currently work as a research assistant under the supervision of Professor Lin Chuanyang at the School of Architecture, Southwest University. Today, I'm honored to share with you a recent study conducted by our team. Mm. In recent years, the global trend of population aging has intensified due to increasing life expectancy and noble birth rates. According to the United Nations, the number of older adults worldwide is expected to reach 1.3 billion by 2050. Japan currently has the highest aging rate in the world, with adults aged 65 and accounting for 29.3% of the national population as of 2024, driven by four major trends: aging population, disability, empty nest families, and no birth rates. China is also facing a serious population aging challenge. By the end of 2023, the number of people aged 16 and above has reached 297 million, accounting for 21.1% of the total population. In recent growing trends of population aging, governments and organizations around the world has introduced various policies and strategies. At the international level, the WHO proposed the concept of active aging in 2002. In China, the 1976 Central Committee stated that the lead to implement a national strategy to actively respond to population aging, marking the first time that aging issues were elevated to the level of national strategy priority. Since then, the importance of this strategy has been repeatedly. Public transit plays a vital role in enhancing mobility of older adults and serves as an essential foundation for supporting the social participation, healthy living, and integration into urban life. And due to age-related physical limitations and the distinct socio-economic circumstances, such as being mostly retired and have more than time, older adults tend to exhibit travel behaviors that differ from general population. Moreover, given its high potential for policy intervention and improvement, public transit has become a key tool in promoting active aging. And passenger satisfaction is a key indicator for evaluating public transit service quality, reflecting the degree to which passengers' perceptions align with their expectations. Existing studies have established metric frameworks focusing mainly on transit and airline certification. However, only a few scholars have paid attention to older adults as a special group in transit certification research. Moreover, current research rarely distinguishes between different public transit modes, such as metro, BRT, and conventional buses. As for methodologies, existing tri-city certification studies typically use correlation analysis, ordinal regression, and path analysis to identify key influencing factors by comparing standardized coefficients. A notable limitation of these studies is the neglect of potential nonlinear relationships between service attribute performance and overall satisfaction. In recent years, machine learning-based methods has been increasingly introduced to explore these nonlinear effects. To address this issue, this study conducted face-to-face surveys with 928 older adults, connecting their satisfaction ratings and feedback on public transit service attributes. Based on source data, 3 random forest models were built to analyze the relationship between overall satisfaction and attribute performance among older adults. Additionally, 3 important performance analysis models were employed using satisfaction and attribute performance data to identify the key service attributes that require priority improvement. The study served older adults aged 16 and above. We selected 31 public tri-city stations as serve sites, conducting questionnaires around these stations or inside viaducts. These 31 stations are located within 5 central urban districts of Chengdu and cover all operational metro and BRT lines, as well as some commissioned buses routes. A total of 950 questionnaires were randomly distributed, with 928 valid responses connected. As the table 1 presents the social demographic characteristics of the respondents. Overall, the participants exhibit balanced gender distribution are predominantly in the younger elderly age groups and have general low education levels and possess moderate monthly incomes. Additionally, the vast majority don't have driver's license. The table 2 shows the means and the standard deviations of attributed performance and overall satisfaction for metro, BRT, and buses services. The data indicates that metro has the highest average overall satisfaction with a relatively small standard deviation. In contrast, the bus service has the lowest average overall satisfaction and a slightly large standard deviation, reflecting relative lower and more varied passenger ratings. Based on the served data, we built 3 random forest models. The figure above illustrated the relative importance of the service attributes influencing satisfaction across the 3 public transit models. And for older adults satisfaction with mutual, the top 3 attributes are transfer time, the complaint handling, and the easy for transfer. In BRT services, the top 3 are transfer time, complaint handling, and station accessibility. For bus, waiting spaces, waiting time, and crowding are the most important factors affecting overall satisfaction. The figure presents the PDPs for the most influential attributes of metro, BRT, and bus services. The results reveal a clear nonlinear relationship between satisfaction and with individual attributes and overall satisfaction. For example, as satisfaction with transfer time for BRT service increased from 2 to 3, the overall satisfaction rises slightly. However, when satisfaction with transfer time increased from 3 to 4, there is a marked improvement in overall satisfaction. This range represents the most substantial improvement in satisfaction. Beyond a satisfaction level of 4, 4 increases in attributed performance have limited returns. Relative importance rankings alone cannot determine the final priority for service attributed improvements. This is because even if an attribute ranks high in importance, its actual performance may already be satisfactory, limiting the impact for the improvements on overall satisfaction. Therefore, these studies introduce the IPA methods to assess both the relative importance and performance of attributes, aiding in prioritizing service enhancements. So, how interpret these results? For instance, transfer time for metro services, waiting spaces for BRT service, and crowding for bus service fall into the secondary quadrant. Identify them as priority areas for improvement. So this study makes 2 main contributions. First, it introduced machine learning methods into public transit certification research with a focus on older adults as a special group. The second, it provides a scientific basis for promoting age-friendly development across multi-public transit models. So that's all. Thank you very much for the privilege of presenting these studies.
Thank you very much. Again, if there are any questions, please post them on the chat. So I have a quick question regarding the survey design. So you focused on the current users of transit, right?
Yes, 3 transit models.
Okay, so I was curious about and I probably I don't know if it's within the scope, but I was curious about people that want to use the service but don't, right? I'm guessing when you're trying from the policymaker's perspective, to try to design elderly friendly transit, you would like to target people that might want to use it. They have the need to use transit, but they cannot for some reasons. I would assume maybe like universal accessibility or but other kinds of barrier-free measures. So have you thought about those users?
Oh, yes, yes. So that's also the focus for these studies, uh, because the older adults um, have some special child behaviors. Uh, we mainly focus on these groups, these special groups.
Yeah, but do you have any insights regarding people that might not use it? I mean, they cannot drive, for example, but
Oh
they
yeah.
have other ways to travel because for some whatever reason that might exist. So
Oh yeah. I'm
what
so
I'm trying to
sorry.
say now, what I'm trying to say, there might be a latent demand for elderly people that want to use transit, but they can't for some reason, right? So they're not included in your sample because you're targeting already people that are using transit, right?
Oh yes.
So that might be an
Oh yeah, yeah.
interesting.
I know. Yeah, I got
Okay.
it. Yeah, so that's is also the one of the limitations for this studies. So we can only just do a serve for some older people that have used this public transit models.
Okay. There's a question from Lynette. So did you observe any differences in preference among those aged between 60 and 70, 70 and 80, and older than 80?
No, no, we do a survey for just um, if the older adults um, is 16 or above, which we didn't distinguish the um, the 60 to 17.
But you have the data, right? So what, I think her question is whether there were differences in
Oh, yeah,
preferences
yeah.
across the age
Uh,
group.
of course, the age groups. So we didn't compare the two groups. We just concentrated on the people about aged 16 and above.
Okay, okay. Lynette,
Yeah.
if you have any insights that you want to share, I don't know if you can unmute yourself.
Yeah,
Uh,
thanks,
oh,
Giancarlos. Yeah,
great.
thank you so much, Hassan, for the presentation. I was just curious because I expect some differences in the behavior. I guess walkability might be a bit more of a challenge for the older age groups. So I was just curious, but it'd be interesting since you have the data. Might be an interesting direction to take.
Uh, I'm so sorry. I
Oh,
didn't
sorry.
hear
Maybe I
your
spoke too
questions.
quickly. Yeah, I'm sorry about that. Yeah, it's not really a question, maybe just a suggestion. Since you have the data, you might be able to look into the difference in the in travel behavior or
Mm,
preferences. Maybe for the much
mm.
older respondents, taking transit might be much more challenging for them. So it might be interesting to take a look.
Oh, okay.
Thank you.
So I think what it's trying to say is like there is in the gerontology literature you usually say like old young and old to try to even among the elderly to try to classify
Oh
because there
yes,
might
yes.
be heterogeneity in there, right? So there might be different preferences. So that might be interesting to look at.
Okay, okay. I know it. Maybe it could be the further studies we could concentrate the old and old.
Okay. Okay. If there are no more questions, are there any other questions? If not, I would like to wrap it up here. Thank you very much.
Thank you.
And then we want to move on to our next presenter, the road to cleaner transit, shaping preferences for electric buses through household education, from the National University of Singapore. Whenever you're ready.
Okay, thanks. I will share my slide. So, can you share? Can you see my screen?
Yes, go ahead.
Okay, okay. Okay, so Hi everyone. I'm Zhi Hao, and I'm the fourth year PhD student in economics from National University of Singapore. So in this paper, we are mainly talks about how to teach Singaporeans to take electric buses. So this is a joint work with my supervisor Alberto and Dr. Tim, also from NUS, and Dr. Y Yan from Land Transport Authority in Singapore. So as you know, Singapore is a microcosm of many other cities around the world. So before I present, I want you to think about one question. So what is the main engine type of Singapore's public buses in your opinion? Diesel, electric, or hybrid? So the answer is diesel. In 2024, there were 6,000 public buses in Singapore, but predominantly diesel buses. Only 8% are battery electric buses, which were introduced in 2020. So before 2040, the Singapore government wants to switch all the bus fleets to 100% cleaner energy. So the government promote the electric buses because of the global and local co-benefits of bus electrification. So compared to the conventional diesel buses, electric buses have several advantages. First, it can help decarbonize the road transport. So we estimate that if we assume all the electricity was generated with natural gas in Singapore, on a life cycle basis, the diesel bus emit about 200 tons carbon emissions per year per bus. In contrast, the electric bus only emit half of it. So the emission reduction per year is equivalent to the carbon stored by 10 mature rain trees. And secondly, the electric buses have zero tailpipe emissions. So this can bring about huge public health benefits through cleaner local air. And there are two other advantages, that is less noise pollution and lower maintenance cost with electric buses. Okay, so in this paper, we want to answer 4 questions. First, while the Singapore government is investing a huge amount of money in electric buses, are the commuters and citizens aware of the benefits? And if does they do the citizens willing to pay for the electric buses? And secondly, we want to know if any educational campaign on the clean bus technology can shape the individual's preferences, thus raising their willingness to pay and finally lead to an increase in the actual usage of electric buses. So to answer these questions, we implemented a large-scale randomized control trial in Singapore. So this is a 4-month educational campaign with 1,200 Singapore households. And we repeatedly highlight the co-benefits of investing in clean bus technology while tracking their public transport use. So there are 3 main findings of our paper. First, the intervention improved the household awareness of bus engine types and the perceived advantages of electric buses. And secondly, our hypothetical choice experiments indicate that the treatment raised the willingness to pay by 10 US cents per bus trip. And finally, the shift in preferences is also observed in the real behavior using the transit payment data. So the main takeaway of our paper is education can expand the support for general environmental protection. Okay, so this figure summarizes the design of our experiment. By cooperating with a marketing company, we recruited 1,200 Singapore households living in a neighborhood which was served by electric buses since April 2020. So our experiment was from September to December 2021 with 7 research encounters. So the first and last of which were conducted in person by a professional enumerator. And between them, we have 5 online interview questionnaires. So at the baseline, the enumerator and household will meet for 20 minutes. So we obtained their consent and then collected some demographic information and also took a picture of their fare card, the transport fare card. And then we let them complete 2 choice experiments, which I will describe in more detail later. And then we ask their general environmental beliefs and attitudes, and also their bus engine type perceptions and satisfaction. So at the end of the baseline, we randomized half of the participants into a treatment group. So the treatment group will watch a short video clips, which introduced the co-benefits of bus electrification, such as reduced carbon emissions and so on. And after the baseline, the participant will receive a personalized link to complete 5 online questionnaires. So the online encounters will repeat the choice experiment and also the bus satisfaction questions. And for the treated household, we play different short video clips for them, but introduce different benefits of electric buses, such as reduced noise pollution and less maintenance cost and so on. So in December 2021, the enumerator will come to the participant's home again and to complete a 15-minute inline interview. So for the treated household, we will recap all the benefits of introduced the benefits of electric buses. And then for all of the participants, we will repeat the question in the baseline, but without the demographic information. Okay, so as a reward, the participants can get the supermarket vouchers worth of 65 Singapore dollars in total. Okay, so this table summarizes the characteristics of our sample. So as you can see, the participants are well educated. So 40% of the participants have a bachelor degree and above. And also 8% are employed. As you know, in Singapore, it's very expensive to get a car. So you can see, on average, our participants travel for 4 days a week and 4 trips a day, but 63% are made on public transport, while only 27% are made on personal cars. And also for households, only about 40% households have a car at their homes. And another interesting point about our setting is there is a feeder line between the train station and the residential block we serve. So as you can see, 50% of the household living close to the electric bus stop, but the other half living further away from electric buses. Okay, so as I mentioned earlier, we let the participants do several choice experiments. So the first choice experiment is about a travel time bus engine type choice task. So there are 2 hypothetical but realistic alternatives, bus A and B. So they are different on 3 attributes: the walking time to the bus stop, the engine type, and also the riding time, sitting on the bus. So this figure gives you an example. So this is one example of a very challenging task because there are 3 varying attribute levels. So based on these attribute levels, the participants just choose the option they prefer. So to reduce the cognitive load, more than 75% of the choice tasks only have 1 or 2 varying attributes. Okay, so as you may notice, in the first choice task, we don't have the bus fare attribute. So we designed the second choice task, which is a very classical value of time choice experiment to calculate the willingness to pay in monetary units. So here we have 2 alternatives, regular or express bus, and they are different on the riding time and the bus fare. So we choose the attribute level to match the distribution of cost per minute of time savings using the estimates from the transit agency. Okay, so importantly, in our paper, we can track the public transport use for some sample of participants because we get the fare card number. So we get the data for 2 years, from April 1st, 2020 to March 31, 2022. And the raw data is at card by trip segment level. So we observe 1 trip, which the entry station and the time, and also the exit station and time. So because of the time limitation, I will skip the statistic part. Okay, so then I will show the results, the three sets of the results. So the first result is we evaluate the impact of educational campaign on bus step perceptions and satisfaction. So we analyzed based on a question that asked the participants to rate the diesel and electric buses on 6 attributes, such as the fumes, the noise, and the climate change impact, and so on. Across the participants, we randomized the order of the comparison. So that means for half of the participants, they will see that on the left, electric bus is better, but for the other half, the electric bus is worse on the left. And then we estimate this regression. So the outcome variable is the satisfaction level on electric bus. And on the right-hand side, we add the video treatment dummy and control the baseline outcome, and also add some participant encounter control variables like this pre-order of options. We also control the data and hour fixed effects. And we also estimate a dynamic version of this regression to show the trajectory of treatment effects. Okay, so this table reports the regression results. The dependent variable is the satisfaction level on a 5-point Likert scale. So we rescale the point such that the 5 always means the participants strongly agree electric bus is better. As you can see, the video treatment significantly improved the bus satisfaction on all the 6 dimensions. And this result is robust to using different samples or using the summary index based on the 6 questions. And this figure shows the dynamic treatment effects. And you can see the treatment effects shows up immediately after the baseline interview. And the effect is persistent until the inline encounter. Okay, then we use the 2-choice experiment to infer the willingness to pay for electric buses. So we build 2 discrete choice models. The first model is using the travel time bus type choice task. So there are 2 alternatives, and there are 6 choice situations, and 68% of the participants completed all the 6 choice tasks. So we have 3 attributes, and the coefficient on each attribute is random. We allow the coefficient to be normally distributed and IID across participants. We also allow the preference on working time and riding time to be correlated. Importantly, you can see the education, the video treatment shift the preference on each attribute. So then the the willingness to pay in minutes of ride time can be calculated as a ratio of 2 betas, beta 1 and beta 3. And then to calculate the willingness to pay in monitor units, we use the second choice task. So there are 2 alternatives, but now we have 8 choice situations. So we have 2 attributes, bus fare and riding time, and we restrict the coefficient on bus fare to be negative by modeling the distribution of a log alpha 1 and alpha 2. Then using this framework, we can calculate the value of time by the ratio of alpha 2 and alpha 1. So therefore, the willingness to pay in monitor unit is just the product of 2 betas and 2 alphas. Okay, so this figure reports the median value of willingness to pay across different participants and different random draws. And on the left panel, we use the pooled sample. You can see the video treatment group, their willingness to pay is 10 cents higher than the control group. On the right panel, we report the willingness to pay by encounters. So at the baseline, nobody has seen the video. So we calculate the median willingness to pay across all participants. And the value is about 10 US cents per trip. But at the video shown, both the video treatment and control group increase their willingness to pay, but the treatment group has a more significant improvement. Okay, finally, we want to see if the preference is also reflected on the public transport ridership increase. So to answer these questions, we aggregate the card by trip segment level data to participant by year week level. And then we estimate a dynamic two-way fixed effect difference in difference regressions. So the outcome variable is just the share of trips on the electric bus in year week T. And on the right-hand side, we have a set of time dummies, which is the gap between year week T and the week in which participant I was recruited into the panel. And we control the participant at year week fixed effect. So this is a very is a staggered DID design. So we use different estimator to get a robust estimate of the event study estimates gamma L. So first, we can see the video treatment doesn't shift the participants from private travel mode to public transport because we didn't have observe a significant impact on the total public transit trips of participants. But indeed, the treatment increased the ridership on electric bus, and the effect is very persistent. We document a positive significant effect even after 24 weeks of the baseline interview. And if we zoom into the specific bus service, bus 944, the result is still robust. And finally, we explore the heterogeneity by car ownership and also the distance to the electric bus stops. And we find that the strongest impact is for the participants without a car, but living close to the electric bus stop. Okay, so to summarize, in this paper, we found that the educational campaign can successfully shift the preference of households. And this illustrates that repeated exposure to relatively cheap educational campaigns can effectively shape environmental preferences and widen support for environmental protection. So this is a very general problem applied to the adoption of any clean technology, which requires the citizen support to sustain. Okay, so thank you for your attention, and I'm ready for any questions. Thanks.
Thank you very much. That was a very interesting presentation. Again, if you have any questions or comments, please write them in the chat. But in the meantime, first a clarification. So you mentioned that in terms of causal effect, there was no causal effect in terms of increasing transit trips, but there was a causal effect in terms of choosing electric vehicles for your transit trips. So people already using transit, they're just using electric vehicles. So how does that work in reality, right? Because I don't know how the fleet works. You have the same bus route that might have a electric vehicle or then a conventional vehicle, but do people actually stop and wait to take the electric vehicle, or they just like how can you elaborate how does that work?
Yeah. So this is a good question, and whenever I present this paper, I will come across such question. So the background of our paper is in Singapore. So as you know, Singapore public buses is very important in our daily life. So there is a dense bus network in Singapore. So suppose I live in location A, and there are two bus stops, B and C. Both are 400 meters away from my home. So the stop B has electric buses, but stop C doesn't have. So our results illustrate that the participants are more likely to choose the stop C to take the buses.
Okay, in the stated preference environment. That's an stated preference.
Yes.
Okay.
The reviewed preference. So that is the observed in our the fare car data.
But it was okay. So it's real preference. So you see that they actually choose to. Also, the bus network is that dense that you have routes that don't have any electric buses, and then you have some that have some electric buses. Is that that's the explanation?
Yeah.
I understand.
Yeah.
That's very interesting. So ultimately, the final policy objective is to electrify the whole fleet, and then you're trying to understand whether these campaigns will just gather support to do that.
So basically, the purpose of our research is to know the preference of Singaporeans on electric buses, so that we can better design the bus fleet structure to serve the residents. Yeah.
Okay, that's very interesting. Thank you. Are there any other questions? If there's no other questions, just a very quick confirmation. When you talk about there was many slides, so I don't remember, but you talk about the regression results where you show the causal effects of video treatment. It was 0.23 or something. Can you show the slide?
Which one?
No, it is back in the, yes, more way back.
This one.
Table, yeah, that one, yeah.
Okay,
So
okay.
finally, so you show the participants in baseline and at least one of the three follow-up encounters. So
Hmm.
how do you interpret this coefficient? Because this is a Likert scale, right? So it's a very not that easy to understand what 0.23 means. So is this a
Yeah,
big, do you think it's a big effect? Do you think it's a small effect?
yeah, so we also report the baseline mean of the control group. So you can see for example, for this index, the Likert score is about 4 in baseline.
Hmm.
So we observe the increase is about 0.2. So it's almost 5%
Yeah.
increase. Yeah, and we think that this is a economically significant impact because you can see the estimate is very precise. The standard error is
No,
very small.
I
Yeah,
don't question the statistical
yeah.
significance. I'm wondering whether you think a 5% is a large effect or not.
Yeah, I remember we also replaced the dependent variable with the proportion of agreeing to the statement. So as you can see, in this question, we can calculate how many participants agree that electric bus is better than diesel.
Okay.
And we did observe that that proportion also increased, but I forgot the specific number, the estimates. Yeah.
Okay, thank you.
Sorry. Yeah.
I don't see any other questions in the chat, so I would like to wrap it up here. Thank you very much.
Thank you.
Then moving on to our fourth presentation, identifying key service quality dimensions of intercity railway service. Mr. Rahman, if you're ready.
Yes. Yes, can you hear me?
Yes, I can hear you. So can you share your screen?
Yes, I'm sharing.
Yes, we can see it. Great. And also, if you can turn on off your video, that'll be great. Thank you.
Okay. Can you see me right now?
Yes, perfect. You can start.
Hello, everyone. Good morning, respected researchers and invited guests. This is me, Mohammad Siam Nur Rahman. My research topic is identifying key service quality dimension of intercity railway service, a structural equation model approach in the context of Bangladesh. This is our presentation outline, which will be start with background and motivation, followed by objectives, methodology, and meta description, and move on to model development, result discussion, key findings and limitations, and future scope. About background in developing countries like Bangladesh, there is a paradox for railway system, basically intercity railway system. It is quite important and economical. It is important for economical growth and other thing, but it is here to fail match with customer satisfaction and it is content with inadequate facilities for customer service. So to understand the background behind it, the traditional methods like usual survey is not quite helpful, so we used a robust measurement to do it. And we used a structural equation modeling approach to find the combination and the key variabilities behind them. The objective of the presentation is to identify and analyze the key dimensions of service quality in the railway industry. to develop and validate a structural equation model that measures the impact of these dimensions on overall service quality. And finally, to identify the most significant latent variable that can be characterized by observed variables. About the methodology, I start with data collection, which is not that large, but is still meaningful, and followed by principal component analysis, which is can be short form as a PCA. Then we constructed SEM, structural equation model, and validate it through confirmatory factor analysis. Then we started to understand the model fitness, how much good it is. About the data description, we have a questionnaire survey which had 4 demographic questions and 21 attribute questions and 1 general questions of honor general questions of about service quality. In these things, is satisfactory. About questionnaire survey, we had the location Komlapur railway station and airport railway station, which is in Dhaka, which is also the capital of Bangladesh. The reason behind these 2 stations was because as the capital of Bangladesh has only 2 railway stations, and it can give us a more diverse situation if we though with a geographic restraint. About demographic information, it has moderate diversity in travel frequency or gender and occupation and age related. Then we had, as I said, that we had like 21 attributed questions, 21 service quality attribute questions. So we started to reduce it. We need to do principal component analysis to latent variables. To check the suitability of data, we had checked Kaiser-Myelin-Olkin ratio or Olkin value, which we had the 0.857, and the acceptable range is 0.8 to 0.9, which is also okay. We also tested a Barclay's sphericity test of acceptance. There our analyzed value was 0.00, which is quite okay, as the acceptable range is 0.05. Our skewness was also in acceptable range, which is 0.904, and the kurtosis was also in acceptable range. Okay. About principal component analysis, we had checked the eigenvalues of those, as we needed to figure out how many latent variables can be extracted from this data set. So at first, we had the split plot. We have seen here the acceptable range is the eigenvalues had more than 1, and we can that much of latent variables. So we can say there are 4 latent variables could be extracted from our data. But if we had taken 4 latent variables, then we have that it was also contradict something like every latent variable had to keep at least 3 observed variables. But if we had taken 4 latent variables, then there it wasn't established. So we have taken 3 latent variables for extraction. Okay, this is our rotated component matrix. In this matrix, as we have seen, we have said earlier that we are going to use 3 latent variables. So we have 3 components, and these are my 21 attribute questions we had asked to the passengers or the users. We have to extract. But before that, we have to understand that each variable can help the model to understand or not. That's why we had some exclusion criteria about these observed variables. As we have seen some literature or in literature review, the loading value less than 0.4 or would be will not be that much help to understand the model. So we have extracted vehicle occupancy and safety in moving train, as they had as there didn't have any significant loading in any of the component. Another problem we have faced that cross-loading means loading in multiple components. And then we have seen the waiting room facility and food qualities. They have very significantly or more than 0.4 loading in both components. So we have to exclude this as this can create an ambiguity in our confirmatory factor analysis or does not help the model to match our fit. So basically, as we had 21 variables, so we had excluded 4 variables because of these two reasons. And so we have the finally 17 variables to work with us for our confirmatory factor analysis. As this is basically the name we have given to our latent variables, as our one of our first and latent variable is convenience and cleanliness, which has 8 observed variables or connected to 8 observed variables. It started with space in moving trains, spacing in among seats, seat condition, crowding level, cleanliness in toilet or cleanliness in station, in train, or a kind of personal behavior. By following that, we have another latent variable named operating efficiency, which is constructed by the observed variable fare service ratio, punctuality, ticketing system, waiting time, journey time, and availability and accuracy of information. And our last latent variable we have chosen as safety and security, which has observed variable as safety of luggage, safety from theft, and safety of women. Okay, this is our final proposed structure equation model we have used. As we have seen here, this is yellow portions are our latent variables, and these latent variables are every one of them is connected with our observed variables, this and this. And finally, we had the question to understand our overall service quality and the effect or impact of these observed variables to the overall service quality by means of latent variables to make it more understandable and easier. We also constructed those lines to understand their covariance and understanding the dependency of latent variables among each other. And these values basically are path coefficient, which had come from our after we had done our confirmatory factor analysis. And these things are basically our error in our measurements shown. This is our model results I'm showing here. As we have seen, we have z value, p value, and coefficient. Coefficient can be understand as their weight on our service quality, about the perception or what people believe. About the latent variables, we can clearly see that it is scaled in 1. So operating efficiency has the highest impact on overall service quality, and among operating efficiency, fare service ratio has the highest impact on operating efficiency, followed by the convenience and cleanliness about has a major impact on overall service quality than safety and security. In our Z values and P values, most of them, basically every one of it has less than 0.05 confidence. So most of them are pretty significant for the model. This shows our fitness of our model. About RMSEA value, here the value is acceptable range is 0.1, which shows a mediocre fit. Basically, the good range is less than 0.08, and SRMR, which has shown good fit here, less than which has 0.08 good fit. And about CFI and TLI, usually it has more than it usually stays at 0.8 to 0.85, but acceptable range is greater than 0.9. But when as in literature reviews of some models, we have seen that if the data set is as much as large, its accuracy tends to decrease. About AIC and BIC, this used basically for, we had tried some alternative models about 2 or 3 things, changing 2 or 3 things. At that time, these are the list values we had with us. About key findings, as we had shared in our objectives, that we are trying to understand the latent variable in this railway intercity railway sector in Bangladesh, and based on the perception of our passengers. So basically, as we have seen, we can extracted three latent variables. One is operating efficiency, cleanliness and convenience, and safety and security. About that, most influential latent variable was operating efficiency. And about operating efficiency, this had almost as is one most important, because people are more concerned by the tail delay or the fare service ratio, or they are not believing they have enough. They are not getting the service they should have by which they are paying for fare. About critical service attributes, as I have as saying, people are very critical about the fare they are paying and about the service they are having. As among the service, there can be multiple things: a train delay, the seating arrangements, or are they having tickets or not. Personal behavior is also an important issue here, because sometimes they are not behave with good people, or they are not occupied with the correct information or easy information from the authority. Safety from threat is also an important attribute, as we can see in third world country that security is also a concept. We also show a different thing, that positive correlations between all latent variables, so which means basically if we increase satisfaction level in one latent variable or one all thing, that can affect the satisfaction in other things too. About the limitations we had, we at first the sample size is pretty less, which is also okay for doing SEM or structural equation modeling approach. But if we want to see the larger picture, we have to increase or make it a more transferable model to similar countries where it is very constrained or a problematic situation. We have to increase the sample size, which can make us a good or larger picture. It can sometimes have potential bias about, as we have just taken questions from 1 to 5, and it can affect the model. Though about CFA and the other things can reduce the covariance. About geographic constraints, as this was data was collected only from the capital of Dhaka, so capital of Bangladesh and Dhaka. So other regions or the opinions of other people or other station, we need to do more than that. About future scope, as we have seen, despite government is trying or the fare they are taking, they are trying to do much, but we have to understand that the people's expectation, does that realistic, or we can do it financial implication on service quality, can we help the satisfaction of the people, and if we move from public to private system, then we have to understand, is it doable or not. And we hadn't explored any impact of technology in here about online ticketing, mobile apps, which that is because not everyone is doing it right now. So we had just excluded it, but it can be done in near future, as lots of people are moving into it. And to understand, as I said, there is a geographic constraint here, so conduct a nationwide survey would obviously recommendable here for the better situation about Bangladesh. As this is my thank you for your time, and if you have any question, you can ask me. Thank you.
Thank you very much. Are there any questions regarding this presentation? Please post them on the chat. Okay, so I have two questions. Well, one question, one comment. So the first one is related to you put safety for women in as an exploratory variable. But I was wondering if that would just be necessary to segment your full model between genders, because I would expect that the perceptions between men and female
Yeah.
will be completely different, right?
Yes, I had done it. It is not shown here, but basically, as we have seen that if we gender-based situation or gender-based model, that's new models. Then there we have seen that if for males they have given more satisfactory, comparatively satisfactory perception than women in this in the data we have.
So,
That
so,
is
so
the
why
gender.
did you decide to combine it to put safety for women as a individual variable instead of segmenting the
Yep,
models?
yep. Combine. That's basically as my undergrad thesis. That's the time I had done this. I did it after that. So that has another model actually, and I had added some about the frequency, the people who are using more train, and that is a more complex model. I just had added it here. That's it.
Okay. Um, and the other thing is a minor comment, but it shows slide 16, the goodness of fit.
Okay, this
Uh,
one.
yeah, that one, right? So you say close to the threshold, but I don't think point 0.8 and 0.83 are close to the thresholds, right? So ideally, you
Uh,
want to be 0.95 and up. And then
yep, yep.
the more relaxed threshold says like 0.90, but it shouldn't go below that. And I think going to 0.8 is a little bit of a stretch.
Oh,
So,
that's basically as I have seen the more SEM models in our Iowa, and I was doing literature review. They are very rare that they see the data set as the data set goes large. It is very rare to see that they reached 0.95. So it stays around 0.9 or 0.85. That's why I have said it.
okay, I would guess that that would be difficult to go to past peer review, but okay,
Yeah.
I agree with the argument. Are there any other questions? Okay, if not, then I would like to wrap it up here. Thank you very much.
Oh, thank you. Thank you. Thank you, everyone.
And then moving on to the final presentation of today and today's session, development of modified approaches for implementable PCUs for Indian road traffic. Whenever you're ready, the presenter here is Sukhjinder Singh here.
So
Oh,
yeah,
great.
Singh is here. I made him co-host and I asked him to unmute himself, but
Yeah, he's on.
yes, he
Oh, there
showed
you
him.
go.
Okay.
Uh, Hello,
Hi.
sir. Am I audible?
Yes, I can hear you.
Yes, sir. So I will share the presentation.
Yes, please go ahead.
Uh,
Yeah, we can see the screen. Can you make it full screen? There you go.
yes, sir.
Yes, go ahead.
Uh, so just a minute.
Okay.
Sir, I think I have the audio recorded PPT, so that is getting played. I will just adjust it. Just a minute.
Okay.
Yes, sir. Sir, I'm very sorry for the disturbance. Actually, that presentation had the video, so I was not able to speak. So I will start the presentation now. Um, Sir, I hope I'm audible and the presentation is clearly visible. Is it so, sir?
Yes, all good. Go.
Yes. So I will go ahead. So I welcome you all for this presentation and a very good day to one and all present in this conference. So my presentation is on development of modified approaches for the implementable passenger car units for the Indian road traffic. So my name is Sukhjinder Singh. I am a research scholar in the Department of Civil Engineering at Indian Institute of Technology, BHU, Varanasi from India. So basically, we are as we are very much aware of the passenger car units. So which are the equivalent factors which converts the heterogeneous traffic into a homogeneous traffic, so that we can represent the um, flow and density in a common unit. So this uh, is done so that the equivalence can be carried out in the road section. Basically, the PCU values vary from region to region, and it also vary over the period of time. So this we cannot consider this PCU values as a single unit, which are defined by the highway capacity manuals of the different countries, and this value cannot be allotted to throughout the single value cannot be allowed throughout the country. So to overcome this issue, um, the revision of the passenger car units using the different methodologies has been carried out. Not only that, even though there are many methodologies suggested by the research articles, still each of the methods come with its own limitations based on the parameters that are considered. So here I have listed out few of the literature works um, which has been uh, studied to carry out this research work. So usually the speed error ratio method, which is called the Chandra's method, is adopted for most of the studies to determine the PCU values. But still, some of the recent researchers have carried out considering this speed error ratio method and have done some modifications with the formula, and then they have suggested that instead of going with the projected area, we can use the effective area, which is based on the size ratio of the vehicle. And another study suggested that instead of considering the projected area of the vehicle, we can go with considering the length of the vehicle, also the width of the vehicle as 1.1 times the width of the vehicle, so that the um, neighboring influence can be also considered. Not only that, in one of the studies which directly used the georeferencing method using the ArcGIS software to directly determine the area of the vehicle or dimension of the vehicle from the um, uh, bird's eye view drone captured uh, photographic frame, and then determine the PCU values. So m- this uh, this methodology was very much um, appreciated, as this eliminates the speed of the vehicle headway calculation, the flow rate methods, which are very much extensive to extract from the video data. Further, uh, uh, many other research articles were referred, and it has been inferred that the values that are mentioned in the Indo HCM are almost similar to the one that has been published in an article in the year 2003. Uh, so there has been a almost a significant time period of 2 decades where the revision of these articles has been not done. So to overcome this problem, yeah, recent framework was suggested, in which the online data from the various vehicle manufacturing websites and the sales platforms were taken, and then the dimension of the vehicles were determined. So based on the previous research studies, the research gap has been defined that the dimension of the vehicle has not been uh, dated for almost 20 years, and no standard method is available for determining the dimension of the vehicle. Also, very less research has been carried out considering the impact of the present day vehicles that ply in the road sections. So based on the research gaps, the objectives has been defined. The very first objective is to develop a standard framework so that the dimension of the vehicle can be determined for the present day road traffic. And the second objective is to suggest a modified approach to determine the PCU values considering this revised dimension and to evaluate its impact on the Indian roads. And the third objective is to compare these estimated values with the one that are mentioned in the Indo-HCM and also with the other PCU methods so that the variation between the PCU values can be observed. So this is the strategic work plan. Initially, the research study was carried out, then the objectives were defined. Then in the ahead upcoming slides, we will be discussing about the field data collection and the extraction. And then from the extraction, the preliminary data, what are the preliminary data that has been extracted and the influencing factors that are important to determine the PCU values. Then how a new methodology has been suggested, and using that new methodology, how the PCU values has been determined, and the comparison with the other studies or the manuals has been will be I will be explaining about that. Then finally, we will be discussing about the macroscopic fundamental diagram capacity and level of service calculation for this various methods. So moving on, it has been observed that for the small size vehicle like the two-wheeler, three-wheeler, small cars, big cars, the dimension of the vehicle that has been determined using the recent methodology is almost varying with the one that has been mentioned in the Indo-HCM. Also, if we observe for the light commercial vehicle, for small size commercial vehicles, there has been no dimension mentioned by the Indo-HCM, whereas for the light commercial vehicle, only one specific value has been mentioned. And to overcome this issue, we have determined the um, dimensions for the for the classified small size commercial vehicle, and it can be observed that this from the pictorial representation that the small light commercial vehicle are of different dimensions. Same was carried out for the two axial and the three axial, where the Indo-HCM defines only a single value for the two axial and the three axial trucks, whereas when the calculation was carried out, it has been observed that the dimensions are varying. Also for multi-axial trucks, where the single value has been provided by the Indo-HCM for the four axle, five axle, and six axle commercial trucks. But as we determined the values, they have been very much significantly varying from the one another. One of the reason was because of the axial length that has been um, uh, considered in the vehicles. Further, the standard framework that was um, defined to determine the dimension of the vehicle was based on the small size vehicles and the large size vehicle. So, based on the weighted average, the dimension of the vehicle was determined, and then based on the number of sample size has been defined uh, as the weight, and the dimension of the vehicle has been defined as the value, and based on that the weighted average has been carried out. And for few of the um, vehicle dimensions, it has been observed that they are of standard dimension only. So for those type of vehicles, the regular standard dimension uh, so for those vehicles, the regular standard dimension was considered. Like for the large size vehicle, the buses, the two or three axle um, uh, trucks, and the multi axle trucks. So these comes up with carrier and the containers. So those have a standard dimension. So those standard dimensions were considered. So further, the data collection was carried out at a potential location at Varanasi in India, and 6 hours of data were collected from the morning peak and the evening peak using a videographic technique. And for the data extraction, we have used a tracer software which defines as the traffic analyzer and enumerator for the uh, data extraction. Further, from the using the using the tracer software, the traffic data like the uh, uh, the traffic composition, the speed of the vehicle volume, and the traffic count were determined. And it has been observed that the small size vehicle like the two-wheeler, three-wheeler, and the big and small cars almost contribute for 80 to 85% of the road traffic for this particular location, and the rest of the composition was shared by the large size vehicle like the buses, two axle or three axle trucks, and like commercial vehicles. So the method uh, usually the speed area ratio method is adopted to determine the dimensions of the vehicle, where here a slight modification was done with the speed area ratio method, where instead of the considering the dimension of vehicle that has been mentioned in the Indo HCM, we have considered here the dimensions that has been determined for the present day road traffic, and the PCU values has been determined. Not only that, for this trial was carried out for the homogeneous coefficient method as well, where instead of the complete area of the vehicle, we have considered the length of the vehicle for determining the PCU values. Also, the comparison with the headway method, the PCU values were determined using the headway method and multilinear regression analysis, and then the comparison was carried out. So here in the highlighted region, we can observe that the PCU values that has been mentioned in the Indo HCM, and the one that has been determined using the speed area ratio method, and the one that has been determined using the modified approach, the values are varying or larger for the small size vehicles like these small car, big car, two-wheeler, and light commercial vehicle, whereas for the large size vehicle the PCU values are increasing. Also, a significant variation was observed in the homogeneous coefficient method, where instead of the area, the length of the vehicles were observed, and the values were very much fluctuating. The reason for this is because of the consideration of only length of the vehicle, which we cannot define, which does not define the complete interaction between the vehicles. So it is suggested that to go with the area of the vehicle instead of the length of the vehicle. Also, in the headway method and multilinear regression analysis, the dimensions were very much varying when compared to the one that has been determined using the modified approaches. Further, the capacity calculation was also carried out, and it has been observed that there has been a 10% decrease in the values uh, uh, for the uh, uh, capacity when this capacity calculation was carried out using the modified approach as compared to the speed area ratio method. The reason for this is because of the smaller PCU values for the small size vehicle, and this small size vehicle contribute for 80 to 85% of the dimensions composition of the vehicle. And when compared with the large size vehicle, since these large size vehicle are lesser in composition, and their PCU values are larger, but still they were not able to contribute the larger section or the composition of the vehicle, so which leads to the decrease in the capacity values. Further, it has been from the current study, it has been inferred that with the increase in the dimension of vehicle, the PCU values are decreasing. That is for the small size vehicle, and for the large size vehicle, the values are increasing. And uh, this necessitates the standardization and updation of the PCU values, also the dimensions of the vehicle that are used to determine the PCU values. Further, it has been also observed that the dimensions has a significant impact on the PCU values, due to which the values fluctuate over the period of time as the um, data collection was carried out in some other location as well, and at a different time period, and the fluctuation was observed. Further, it is highly suggested that we have to go with the the revision of the dimension of vehicle, since at the present scenario, the road traffic have significantly changed, and the vehicle dimensions have also been different from the one that has been mentioned in the previous manuals. So finally, the future studies of this research will be used for framing the policy recommendations and regulatory guidelines for the manuals such as the Indo-HCM and the codal provisions like IRC, which defines the TCU values as well as the dimension of the vehicle. So the present research study will be very much useful for suggesting the PCU values for the varying road sections, or as well as the it will be suggesting the framework to define or determine the dimension of the vehicle for the present road traffic. So here, these are the enlisted references that has been used to carry out this research work. Thank you. This is all about my presentation. If we have any queries, we can discuss it.
Thank you very much. I think we're a little over time, but we have some time for some questions. So if you have any
Yes.
questions, can you please post them on the chat? I have a very simple question. Can you show the fundamental diagram slide? I think it's 13 or yeah. So you show the projection, right? That you have in the continuous line, right? But that line is based on half of the diagram only, right? So I don't know if that is an accurate depiction of the diagram because you don't have enough data, right? You don't have data that's 60 and over.
Sir.
So what do you
Yes,
think
sir.
about that?
Yes, sir. Since sir, actually, one of the limitation of this research study was that we have not carried out the data collection for a complete period of time. At least it was many suggestions we have received that we should have gone with a 12 hours data recording or much more. Since we have covered only the peak hour, that is in the morning peak and the evening peak, and from those collected data, we have plotted this diagram. So that we have observed it, and we will be rectifying this issue in the further studies.
Okay, but I think yeah, I think the showing the percentage difference in capacity, like a reduction of 11%, yeah, that's a very interesting finding. So compared to the you mentioned the Indo HCM, so Indo Highway Capacity
So,
Manual, and then what how do they calculate? I was not maybe I missed the explanation, right?
sir,
Compared to
sir,
Indo Pro.
here yes, sir. Yes, sir. So these are the dimensions of the vehicle that has been mentioned by the Indo-HCM. Sir, they have carried out a few of the uh, research studies, and they have determined the dimension of the vehicle. From the video data, they have determined the dimensions. Means they have observed that type of vehicle, and then from the field, in the field, they have measured the dimensions of those vehicle, and they have defined that these are the dimensions of the particular type of the vehicle. But these dimensions were defined in the 2017 or 18 time period, and these dimensions were almost equivalent to the one that has been mentioned in a research article that was published in the year 2003. So there were very not much significant variation between these two, even though there has been a time period of some 15 years. At present, when we have carried out this research study and we have determined the um, dimensional vehicle of the present day road traffic, and we observed a significant variation. So we are suggesting that we should go with the revision of the dimension of the vehicle.
Okay, thank you.
Yes, sir.
Oh, there's a question from Nasser here. So considering few points, yeah, that was exactly my question, my first question,
Yeah,
right?
yeah. You said that. Yes, that was my question as well. Yeah.
So
Yes, sir.
it's answered. We need more data, right? That was
Yeah.
the answer.
Yeah.
Okay. Are there any other questions? Okay, if there are no questions, then I would like to wrap this session. And this is the end of BTR for today. And join us tomorrow for the continuation. And if you still have the energy, you can join in a couple of hours. The Western track is going to start, I guess, in 5 or 6 hours. So there's Marianne and there's also Ben Akiva. We'll be talking. I don't know who's presenting first, but a very interesting set of panelists on the other side as well. So if your sleep patterns allow for it, then I recommend you to join. Okay, thank you very much.
Thank you, Dr. Gian. Well done. Thank you very much.
See you guys tomorrow.
See ya.